Every single time you tap on your phone or stream a movie or even just send a quick email, you're actually using a secret language. And nope, it's not built on words, it's built on numbers. So today, we're going to learn how to translate it. We're going to take the computer's native tongue and make it something we can all understand. Let's dive right in. I mean, have you ever really stopped to think about it? Why is it all just zeros and ones? We're surrounded by this super complex, amazing technology, right? But deep down at its very core, it's all just a bunch of zeros and ones. How in the world is that even possible? Well, stick around, because by the end of this, you won't just know the answer. You get exactly how it all works. Okay, so before we jump into the deep end, let's start with what we already know. We need to start on familiar ground. You and I, we live and count in a world that pretty much runs on what's called base 10. It feels totally natural to us. But here's the thing. It's really just one system out of many. So what is a number base anyway? It's actually pretty simple. The base is just how many unique digits you have to work with in your counting system. For us, in our everyday lives, we use the decimal system, which is base 10. Why? Because we have 10 digits to play with. 0, 1, 2, all the way up to 9. And once you hit 9, what do? You just stick a 1 in the next column over and start back at 0. It's the system we all learned back in grade school. All right, now, let's leave our world behind for a second and step into the world of a computer. See, computers don't have 10 fingers to count on like we do. They have something way, way simpler. Think of it like a light switch. It can only be in one of two states, on or off. And that simple on or off idea, well, that leads us directly to the language computers speak, binary, or as we call it, base 2. It only uses two digits, 0 for off and 1 for on. It's that simple. For a machine that's basically just a massive collection of these little switches, this isn't just a good way to represent information. It's the only logical way. It's direct, it's reliable, it's perfect. And this is where things get really interesting. Take a look. On the left, you've got our good old base 10. We see the number 5, we write a 5. Makes sense. But look at the right. In the computer's language, base 2, that exact same value is written as 101. Now, at first glance, that might look completely random, right? But I promise you, there is a rock-solid logic behind it. And that's exactly what we're about to crack open. Okay, time to put on our translator hats. First mission, we're going to learn how to decode the computer's language. We're going to take a binary number and translate it back into our familiar, cozy base 10. And listen up, because here's the secret. There's one simple rule you got to remember for this. If you ever want to convert a number into our base 10 system, the magic ingredient is always multiplication. That's it. Let me show you how it works. So let's take this binary number here, 1101. The first thing you do is you start all the way on the right. For each digit, we're going to give it a place value. And since we're in base 2, these place values are all going to be powers of 2. Once you've got that figured out, it's just a simple game of multiplying each digit by its place value, and then you just add everything up. Easy. And check this out. This table lays it all out perfectly. If we work from the right to left, you see we have a 1 in the 1 spot, then a 0 in the 2 spot. We can ignore that one. Then a 1 in the 4 spot and another 1 in the 8 spot. So all we have to do is add up the places where we see a 1. That's 8 plus 4 plus 1, which gives us 13. So when a computer says 1101, it's really just saying the number 13. See? It's not a different number. It's just a different way of writing it. Okay, nice work. We've learned how to decode. We can read the computer's language. So what about the other way around? Let's try encoding. How do we take one of our numbers and translate it into binary? This brings us to our second big rule, and it just makes perfect sense. If multiplication is the key to getting to base 10, then it stands to reason that its exact opposite, division, is the key to getting from base 10 into another base. And the method we use for this, it's called repeated division. Let's go backwards with our number, 13. What we're going to do is just keep dividing it by our target base, which is 2, over and over again. And with every single division, the most important piece of information is the remainder. You just keep doing this until your main number hits 0. And then here's the really cool part, the little magic trick at the end. You take all those remainders you wrote down and you read them from the bottom up. That's your binary number. You can see it right here. We start with 13 divided by 2. That gives us 6 with the remainder of 1. Okay, so we take that 6 divided by 2 and we just keep going all the way down until we hit 0. Now for the big reveal. Let's read those remainders in bold, starting from the bottom and going up. What do we get? 1, 1, 0, 1. Hey, we're right back where we started. It works perfectly. So at this point, you might be thinking, okay, that's a cool math trick, but why does this actually matter? Well, let me tell you, this is so much more than just theory. This is literally the fundamental operating system of our entire modern world. Yeah, this isn't just some party trick for mathematicians. When you get how these different number bases work, you're basically seeing the source code of reality. You're seeing the fundamental logic behind every single piece of digital tech you use. It's like having the key to understanding how our world is actually built. And believe me, this system is absolutely everywhere. It's the literal ones and zeros running the app you might be watching this on right now. It's inside the unique SSID number that your phone uses to find your Wi-Fi network. It's even the basic logic that makes your calculator work. And you know, in places like Nigeria, this exact same system is used to generate and check bank account numbers. It really is the invisible framework that holds our digital world together. So I've got a little challenge for you to make this all real. Take a number you know by heart, your age, and try translating it into binary using that division method we just learned. Find out what your life looks like in the language of computers. Give it a shot. Thanks so much for hanging out and digging into this with me.